Welcome, welcome. So today is actually going to be the final stream, basically, for this year. So if you look at the schedule, we normally stream on Wednesdays and Fridays. So today is a Wednesday, so I'm streaming on today. I will also be streaming this Friday, but I'll get back to that in a second. And then normally I would stream the following Wednesday, but that is actually the graduation day stream, and so they've canceled all educational streams for that day. And then that Friday would be the last day of school, and they've also canceled streams for that day. So my plan is for this Friday to have a bit of a get together. Maybe I'll actually do a Zoom call or a Google Meet, whichever one I find seems most reasonable. And we'll play a game or maybe share some stuff. I haven't exactly figured out what exactly I would like to do, but I would like a chance to say goodbye to everybody and wish everyone a good summer and maybe talk about some social issues that are going on. So I'm going to send out a survey probably later today going over that and just gathering people's ideas. Okay, but for today, if you're watching, I'm going to be basically just going over pH calculations. So that's what I have in my agenda. The stuff for physics this week is not difficult. It's very simple. It's basically just watch a video and answer some questions. Wanted to keep it simple. And then, unfortunately, for chemistry, it's the opposite. This is probably the hardest stuff we've done in a while. And so it's understandable that people are going to be having trouble. So I'm going to go over that right now. So this week we are looking at pH. So if I go in here and I click on modules and week 7 homepage, bam, here we go. There's a little video. The very first thing that it asks us to do, preview, is this pH FET. So I'm going to go through basically the FET. I'm going to go through a couple of different types of problems and go over the practice exit card. And then hopefully with that, you will be able to be on your way. Let's see if there's anyone in the... No comments in the chat at the moment. Okay, so you come in here, click on macro. If this embedded link doesn't work, you can probably Google this and it will come up. But the embedded one should work. You might have to accept Flash Player. Okay, so here we have, there's a lot going on the screen, but you can see here I've got a little container with some water, right, which I could fill up with some more water. That's great. What's the point of having this water? Well, if I put this little thingy in here, which I can click and drag around, it'll tell me the pH of whatever it's touching. So the air doesn't have a pH, but once I put in the water, you can see that as a pH of 7. Okay, so that's what that does. Let's see what's going on. It says, begin with, the container will be filled with water. Click the green circle and drag it into the container, and it's basically just showing you how to do this. So I drag it into the container, and it's got a pH of 7. So the answer to this first question is easy. It's 7, or 7.00. Those are the same thing. In fact, the answer will just delete it to 7, because those are the same number. Okay, so that's for water. We know water is a pH of 7, which is right in the middle of this acidic basic spectrum over here. So right in the middle of 7, that means neutral. If the numbers are bigger, that's basic. If the numbers are smaller, that's acidic. Okay, it's just switch over to drain cleaner. Now, if you watched our videos previously or did some other stuff, drain cleaner is a soapy thing that we use for cleaning stuff. I'm thinking this is going to be basic. And in fact, if I put in my little pH meter again, it tells me that it's got a pH of 13, which is way up here in the basic range. So drain cleaner is definitely basic. And it's got a pH of 13, so I put that in there. And then next, because it has a very high pH, it's basic, so I'm going to click base. Now, what I'm going to do is, I have this drain cleaner and I'm going to add some water to it. I'm going to dilute it. Wow. And so by diluting it, I'm going to, well, we're going to see what happens to the pH. but I want you to make a prediction in your brain if you're watching this as to what's going to happen. So I've added a little bit of water. You can see over here the pH is going down a little bit. So the pH is getting smaller, which means it's becoming more, you might say it's becoming more acidic. But more accurately, perhaps, it's becoming less basic or more neutral. Okay, so now we're going to do the same thing, but we're going to use blood instead. So here's blood. I put in this thing, and it tells me the pH of blood is 7.4, so very, very slightly basic. So blood, here we go, 7.4. Is it an acid or a base? Really, the best answer here is that it's neither, that it's basically neutral, but it is very slightly basic. We'll do coffee next, it says. So this is really just a way of testing virtually these different things. Coffee is a pH of 5, or obviously not every cup of coffee in the world has a pH of 5, but this is a reasonable pH for a cup of coffee. And because of that, coffee is a bit of an acid. And we're going to add some water to the coffee. Again, like we're diluting our coffee. Like you got some coffee and you're like, woo, that's got some kick to it. You add some water to cool it down. And what's happening to the pH? pH was 5, and now it's climbing slowly. Until I run out of space in my thing. What's going on with that? So this time, the pH went up. If you look back previously, when I did it with drain cleaner, the pH went from 13 and it got a little bit smaller. Now I started at 5 and I'm getting a little bit bigger. So the opposite thing is happening. Increase, go up. These questions got a little bit out of order. So we know coffee is an acid, and then it says also to check soda for some reason. So we're going to go in here, we're going to click soda, soda pop, bam, even more acidic than coffee. And then just to show you, if I open this water plug, the pH again is going up, but previously it went down when I did it with drain cleaner. Again, watch this pH meter over here. Bam, it's going down. So is there something special about drain cleaner that causes it to go down when you add water versus the other one does go up? Is there a chemical reaction going on? I'm not sure. Let's try hand soap. Hand soap is a pH of 10. If I add water, is it going to go up or down? Well, it looks like it's going down. It's a bit of a conundrum, really. Oh, pH of soda, I forgot. I think it was 2.5. So in number 10, question number 10 really gets to this. It says, think about what you did to answer this question. Go back and play with the simulation, you need a refresher. What effect does adding water have in all the solutions? Well, sometimes it went up and sometimes it went down. So if I was trying to say something more concisely, the only answer that makes sense is this one. It makes the pH move closer to 7. As I add more water, the solution is going to become more like water. And as we all know, water is neutral. It's got a pH of 7. So if I add more water to a solution, it's going to become more and more and more like water, which makes sense. So if it was already basic, it's going to go down closer to 7. So it's going to be going down. It was already acidic, and it's going to go up, again, closer to 7. So that's the real gist of this activity. So if I submit the quiz, I should have gotten everything right. Bam, 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 bam. Correct. Okay, so that's the first thing. That's just a really conceptual thing. Okay, now there's a bunch of notes. You need to watch these videos. I'm going to walk through how to do the problems, but I'm not going to repeat what's gone over in these videos because Mr. Ellingson put some work into putting them together and they're perfectly fine. I will, however, go over the practice problems. So I'm going to show you how to do the problems, but I'm not going to go through the whole notes. I'm just going to do it more problem-solving oriented. Okay, so preview the quiz. Bam. Okay, first of all, you have this diagram. So all of these big bold letters, these are all things we might want to find. If I have something in square brackets, that means that it is a concentration, which if you paid attention in the solutions unit, you know that that means it is a moles divided by liter number. It's measured in molarity or moles per liter. And it's telling you sort of like the density or the concentration of either the H+, so the acidy things, or the concentration of the OH-, hydroxide, or the basic E things. Okay, so that's a concentration. However, if you've done some of these problems, you know that this number can be very small, like 0.0000003. That's an annoying number to work with. So we found basically another way of expressing the same number. pH is just a special way of expressing the H plus concentration. And I mean, look, it's got H in it. It's got an H. We even capitalized the H, so we recognize that it's not just like the letter H. It's like a hydrogen atom, or an H plus. So pH. Yeah, I used to know what the P stood for, but I forgot. But basically, the point is, I've found a way to express this tiny number with a single number. And basically what I want to say is, okay, instead of using this number, I want to use the exponent that would give me this number. And so the way to do that is by using the log function. So if I have this concentration and I'm trying to find the pH, I want to go from some tiny small number that's difficult to write down to an easy number that I can write down. It still means the same thing. And so I'm going to use the logarithmic function of H+, and then I'm going to get my answer. So I'm going to show you how that works. Hey, what's up, Sebastian? So I don't know if you saw Sebastian earlier, but today's going to be the last stream. And then on Friday, we're going to have a bit of a, I'm going to do what I talked about last week. We're going to have a bit of a get-together. So I'm going to send out a survey later today after I finish streaming, asking what people would like to do for that, and if they'd be interested in doing that. And then we'll move on from there. But yeah. Okay, so here's the problem. What is the pH of a solution that has an H plus concentration of 2.5 times 10 to the minus 4? Okay, so this number is annoying and small and hard to write. And so I'm just, instead of using the whole number, if I was to write this number out, for example, by itself, it'd be 0.00025, I believe. That's an annoyingly small number. Okay. Oh yeah, Sebastian, I'll send you, maybe I'll send you an email after I'm done, and then we can talk. And then if you want to do a Zoom, we can. That's fine. Okay, 0.00025. So what I do instead is I can open up this calculator. So there's a link here, which pulls up a calculator. And imagine I just took the log of that number. So 0.00025. It gives me this number, negative 3.6, and there's a bunch of other stuff, but I can ignore that other stuff. I don't need all those decimal points. In the first example, if I just rounded it, imagine me rounding this number to like 2 decimal places. I would just get the number 0. That's a useless number, because I know the number isn't 0. It's some small number bigger than 0. But in this case, even though the number is small, it's an important number. So I want to change the... I basically want to change the way that number is being expressed. Hey, Torian. You should be able to go back and see how I started. So I started just with the pH simulation. So if you can't watch it now, you can watch it. It's after I'm done. But just to catch you up with what I'm doing now, basically I'm just talking about what pH is. pH is just another way of expressing this concentration number. So that H plus in brackets is telling you its concentration. And so this number can be really, really small. So in this case, it's 2.5 times 10 to the minus 4th. That's a very small number, and it's a confusing number because you might accidentally round this number. If you saw 0.00025, you might round this number to 0, and that would be a mistake because even though the number is small, it's an important number. It's representing the concentration. And the concentration is small, but it's not 0. And so instead of measuring, for example, the concentration of H plus in just water is 0.000000001. I think that was one too many zeros. Not only is it like really small, but it's like hard to count and annoying. And so we use pH instead to help us represent the same number, but just looking in a different way. So it's not like we're calculating something. It's not like we're taking some, it's not like physics where you have the mass and the acceleration. You multiply them to find the force. We're just expressing something in a different way using logarithms. So the way I do that, logarithms do a really good job of expressing small numbers as normal-sized numbers. And so this was the example I gave. So if I take the log of 0.00025, it gives me negative 3.6. So that's it. Negative 3.6. Almost. Now, here's the thing. If I use a really, really, really small number, the log function is going to give me a negative answer. That's okay. There's nothing wrong with negative numbers. But because negative numbers, it's weird to get a negative number from a positive number. So I started with a positive concentration. So even though this number is small, it's a positive number. It's weird to then get a negative answer. So instead, what they decided to do is to slap a little negative sign in front. So if you look at this formula, pH equals negative log of H plus, they just said get rid of the negative sign and just make it the positive version of whatever the answer was. That's the pH. So it's just this number, 2.5 times 10 to the negative 4, but I plugged it into the log function to give me something that's a little easier to say. 2.5 times 10 to the negative 4th, that's hard to say. 3.6, easy to say. So it's all about ease of communication. And it's comparable to other things, whereas this is sometimes hard to tell the difference between the numbers. Okay, next. Now, that's for finding the pH from the H+. If I want to find the pOH, it's the exact same thing, but instead of starting with the H+ and going to pH, I just use the log function again, but this time with the OH concentration, and find the pOH. So the process is the same. So I have 3.4 times 10 to the negative 5, so I'm going to Control C that. I'm not sure that'll work, but I'll try. Yeah, I don't like this calculator. I don't know why. I very much prefer just using the calculator function on Google because it works perfectly well. You can even just Google this number up in the top, and it'll just give you what it is. Oh, okay, never mind. It didn't work. Anyway, okay, so I'm going to take, instead of just putting the number, I'm going to say log of the number. So here's a number, 3.4 times 10 to the negative 5. So I got to learn how to put that on my calculator. So there's a few ways. 3.4. Now you could do times 10 to the negative 5. I prefer to use this exponentiation function. Why not a TI? Well, no, in real life I'll use a TI, but I mean, like if I'm using a computer, then I'll just use the calculator that's on Google. It's fine. So this exp function works perfectly fine. So again, the number was 3.4 times 10 to the negative 5. So I just have to do the exp and then minus 5. Minus 5. Just like this. That is the whole thing. I just take the number and I put it in the log function. And then when I hit the equals key, something's going to pop up. Oh, look, it's some number. Now, you might be saying, oh, this number's annoying. Look at all these digits. Don't use all the digits. Just use like the first couple. So instead of writing negative 4.4685210, it's like, forget that. Just use the first few, round it. If you'd like, maybe just round this to 4.5. So minus 4.5. Beautiful. Okay, then you need to remember to not use the negative number. So just get rid of the negative sign. How easy is that? So it's one function. You don't need to know how logs work or do any algebra or anything. You just have to plug the thing into a log function. Very easy. Okay. Now, I think the next problem is going to have us... Okay. The other thing that's magical about pH is that the pH number here and the pOH number for the same solution will always add up to 14. Mind-boggling. Why is that? Go watch the videos. You'll find out. But... So if I'm trying to find one and I already have the other, I don't have to use any log functions at all. I just have to use subtraction. So if the total is going to be 14, and in this case, one of them is already 13, well, what number do I need to add to 13 to get 14? 1. 1 plus 13 is 14. Or another way, 14 minus 13 is the number 1. So that problem's pretty easy too. If this number was some other number, like 10, well, then what number plus 10 equals 14? The 14 is the magic number. And so, 10 plus 4 is 14. But in this case, 1 plus 13 is 14. That's all that's going on there. Beautiful, easy. And that's this formula up here in the top is written to help you remember that. Here's another example. So I got 4.5. So what number plus 4.5 equals 14? Or another way of writing that, or another way to put in your calculator if you're afraid of doing math, 14 minus 4.5. So I'm trying to find the difference between these two numbers, and it gives me 9.5. So I put in 9.5. It actually doesn't matter if I'm going from POH to PH or PH to POH. It's always just finding the two numbers that add up to 14. It's like a little puzzle. Okay, that's that. And then now, here's the only part that's annoying, is going backwards. So let's say that we found an easy way to express concentration. We're like, hey, instead of using these tiny numbers, 0.000025, let's use these pH numbers. So we're throwing around 4s and 7s and 2.6s. And we're like, oh, these numbers are great and nice and easy to understand. But then someone said, hey, I want to do some more chemistry and stuff. I need to know the actual concentration. How do I turn the pH, this number you made up, back into a normal number that I can use for like doing math? And it's like, oh, well, crap. I got to go backwards. So the formula is right here. In order to go backwards and find the H plus concentration, I have to put that pH in the exponent, which is a little bit confusing. So I'm going to show you how to do it. This is just what we have to do if we're working backwards. So I'll say I want to go 10. I'm going to click this X to the Y button, which pops up a thing. Or in this calculator, how do I clear everything? Let's see. I'll do 10 to the, there's a button here, bam, and 10 to the negative sign. Wait, it didn't do it. 10 to the negative, oh, I have to use this negative sign. That's weird. 10 to the negative, and then whatever the pH was. So 1.2. Again, remember how like the pH kind of gave you a negative number, but you forgot about it? Well, now when it goes back to turn the thing around, you got to turn the number back negative before you slap it in your equation. So minus 1.2. And then that's it. And then it gives you back the gross number you were trying to get rid of in the first place, 0.063. So the answer is just 0.063. So 10 to the minus pH. So the pH becomes the exponent to the number 10. I bet you can see where I'm going with the next problem. I'm going to do the same thing, but with OH minus. So same way as I took OH minus and turned it into pH by just slapping the log function, I have to undo that. And the way I undo that is by using this 10 to the whatever power. So I'm going to go to my calculator, clear everything. 10 to the negative, because we just got to do that. Got to flip the negative in there. And then I just put in whatever the POH number was, this 2.4 number. To the negative, 2.4, bam, 0.00398. 0.00398. And I could round that if I wanted to 0.004, but I just put it in the way I did. Okay, that's it. Okay, now, that's the easy part. Sometimes the problems get a bit harder, and this is an example of a challenging problem. If you understood the part that I just went through, you're basically good. You may or may not be able to do this problem, but this problem is not the most important. Now, how do I do this? It says, what is the pH of a something solution of lithium hydroxide? Now, this is really chemistry. someone says, hey, this solution I made by dissolving these many moles in these many liters, that's giving you a concentration, I would like to be able to predict, without anything, what pH it would have. That's the power of chemistry, is understanding what's happening at the molecular level, and therefore how many OHs or pHs or Hs or whatever are going to be floating around in my solution, and then using my understanding of concentration and pH to come up with some number that I can use to communicate with people. That's the power of communication in science. So, it might be useful to have like a little, maybe I'll open up a notepad. Bam. Can you guys see that? Yeah. Okay. So I got lithium hydroxide. What's happening to this lithium hydroxide? Well, when lithium hydroxide goes into solution, it dissociates. So the lithium's going to pop off is lithium plus 1. And then the other thing that's going to pop off is an OH minus 1. So this is going to split into 2 parts. Now, I didn't just have one of these. Now, if I had one of them, you'd get one lithium and one hydroxide. But I didn't have just one of them. I had 0.65 molar of this whole thing. So it's split into these 2 different things. This is probably too small for you guys to see. How do I zoom in? Or make it bigger? View, zoom, Control plus, okay. Control plus. Okay, better. So this is what I have. I have this concentration of this chemical, which has really a few things in it. When it dissociates, I don't get half of 0.65 of this and half of 0.65 of this. It's like saying, let me find a good analogy here. Oh man, this is hard to say. I'll come up one in a second. Okay, so if I have 0.65 molar of lithium hydroxide, then when it dissolves, I have 0.65 molar of both lithium and 0.65 m of hydroxide. Again, m stands for moles per liter. So if I imagine I have 1 liter of this, then this just means moles. Right? So this is basically the concentration. In this 1 liter, I have 0.65 moles of this. When that breaks apart, well, every 1 mole of this contains 1 mole of this contains 1 mole of lithium and 1 mole of hydroxide. So it's like I'm getting 2 for the price of 1, basically, because I'm splitting apart something that was bigger into smaller pieces. So I don't care about this part. Lithium doesn't do anything to the pH. There's no OHs, there's no Hs, it's just a random ion. Useless. However, this over here, this hydroxide, is going to affect the pH. Or in this case, by making it more basic, because hydroxide, OH minus, is a base. I'm trying to explain this as slowly and clearly as possible. So, if you have questions from what I'm saying, let me know. Okay, we just learned how to take the concentration of OH and turn that into POH. How do we do that? We use the log symbol. So this is the one I'm going to use. Just copy that. That's the one. I'm going to use the log function to slap this whole thing in there. Right? So I'm going to take log of 0.65. So here we are, log 0.65. Bam. Okay, so log 0.65, this gave me negative 0.19. Beautiful. Now, as we said, I want to get the formula actually has a negative in front of this, just to get rid of this negative at the end. But it's really easy. If you ever do the pH formula and you end up with some negative number in this class, you just forgot to put it. It's very easy. Just change it to the positive number. Don't need to do anything else. You don't need to redo it. Just put the positive number down. That's all. So this is the POH. How do I know it's the POH instead of the pH? All I did was take the log function. How did the log function know which formula it was doing? It doesn't know. It could never know. It's just a log function. You have to know that because you were taking the moles of hydroxide, it's going to give you the P hydroxide, or the POH. This OH, that stands for hydroxide. Okay, however, now you have to read the problem because you're a good student, and it doesn't ask for the P hydroxide. It asks for the pH+, or the pH. So you have to use another step. There's a two-step problem. So I got this POH, it's great. My POH equals 0.19. However, that's not what the problem asked me for. The problem asked me for the pH. So the pH, well, what's that? Well, I have to use this other formula up here. pH plus the POH equals 14. Remember that magic number thing. So I know that the pH plus the POH equals 14. If I want to find just the pH, algebra dictates that I should subtract. So I should have 14 minus the POH. Find the difference between these numbers. Now I know what the POH is. It's this. So 14 minus 0.19. I'm going to put that in my calculator. 14 minus 0.19. 13.81. So then this whole thing is 13.81. That's the pH. Notice, if I had used the POH instead of the pH, like if I just plug this in as the answer, it's way wrong. Instead of a number like 13, I get a number smaller than 1. Big mistake. Notice also if I just plugged in the concentration of the OH, that would also give me a number that's wrong. 0.65, that's not the right answer. So I have to go through a couple of steps here to get an answer that makes sense. And the best thing about this answer is that it's a big number. This is a number much bigger than 7. That tells us that this must be a base, which is accurate because the chemical I added was lithium hydroxide, and we know from our previous lessons that chemicals that have a hydroxide at the end are bases. So everything works out. We took a chemical that we knew was a base, we had some known concentration, some known number of moles divided into some volume, and then we were able to realize that when this splits apart, I'm going to get the same number of moles of just the part that I care about. So this dissociates, and I did this. And then I know I can use my log function just to slap that in there to give me the POH. So go from the OH concentration to the POH. And then I know that if I really want to find the pH, which is the number that people use to communicate, I need to do this thing with 14. There's a magic number 14. I add them up together. So I said, okay, what plus 0.19 equals 14? Well, 13.81. And then that's my final answer. Okay, that was a lot of talking. There's probably another problem on here, but I don't want to do it. Yeah, this problem, who cares? Is there another one? That one we already know how to do. So all of those problems are just like that. It's fine. Sometimes you don't have to do the math. You can just look at them. And this will be the last thing I go over. So you can look at the numbers qualitatively. You don't have to plug them into a calculator, as long as you can tell the difference between the numbers. So here, it says which solution is more acidic. It's got HCl, HF, and HI. Each of these are acids. How do I know they're acids? Because there's an H in front, right? HCl, HF, HI. Let me delete this. HCl, HF, HI. All three of these are going to split up into their constituent parts. So you're going to need an H plus a Cl minus. It's going to split up into two pieces. This is going to do the same thing. H plus F minus. Okay? H plus, plus, I minus. We're all going to split up. Notice that each of these, bam, 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 has an H plus, and one H plus. Now, I started with some solution concentration of the whole chemical. How do I know how much of that is going to turn into H plus? It's 1 to 1. If I have one of these, and I break it in half, I'm going to have one of each half. Right? So if I have 0.75 of this, then I'm going to have 0.75 of this, and I'm going to have 0.75 of this. Now, do I care about the 0.75 of Cl minus? No! It's not an H plus or no H minus. All I care about is the H pluses. So this 0.75 H plus, that's going to be the concentration of H plus. And it's the same as the concentration of the original acid. It's beautiful. The same is going to be true for all of these. This is 0.5. It's going to be 0.5 of this. I can basically delete the second half of each of these equations. I don't care about them. Get out of here. Don't care. And then this one, I had 0.25. And that's going to give me 0.25 of this. Bam! You seen where I'm going with this? Now I know the concentration of H+. That's all that I need to determine my pH. Now, I don't actually even need to find my pH, because I know that the bigger a concentration of an acid, the more acidic it is. But just to show you, I'm going to go through and do the calculations quickly. So I'm going to take the log, the minus log, oops, clear everything, minus log of 0.5 gives me a pH of 0.3. Oops. So this gives me a pH equals 0.3. I can do the minus log of the other one, 0.75. Gives me 0.12. Dang it. 0.12. And then the pH of the very last one, minus log of 0.25. It gives me, oh, geez, let me get that in there. Minus log of 0.25, 0.6. pH equals 0.6. If you didn't believe me, notice which of these has the smallest pH. The smallest pH is the most acidic, the furthest away from 7. So the one that's the smallest pH is this. 0.12 is smaller than these. Don't think that 0.12 is bigger. Whew! I see that way too many times. 0.12 is not bigger than 0.6. I know 12 is bigger than 6, so that's not how that works. This is really 0.60. That's 0.30. So 12 is not bigger than 30 or 60. Anytime you get confused like that, it's helpful to put the extra zeros on the back. So 0.12 is going to be the smallest. This is going to be the most acidic. And it comes from the fact that the HCl had the highest concentration. And that concentration turns into the H plus concentration. Beautiful. Next! And then, which of these is more basic? Well, this is obvious. We just know whichever one has a higher pH number is the most basic. So that one's simple. So I think question 10 was really important there for people to understand, which is why I went spend some time going over it. So that's basically it. Yeah, I know I didn't answer all the questions. Let's see if I got them all right. Correct, correct, correct. Unanswered, unanswered, correct, correct. So I did them all right. So those answers I give you were correct. So if you're working through it, you should be able to plug those in. And then the last thing is that it's just another hexacard, but it's the same. It's the same hexacard, basically. It's the same formulas, same strategies that we just went over. So yeah, best of luck. If you have specific questions, let me know. I'll try to help you. Survey going out this week for what to do on Friday. That'll be our last meeting. Hopefully you enjoy yourself. And then, yeah, that's it.